Now, going on to your colleague, we have the next talk from a fellow student at the University of Luxembourg. No, I hope I pronounced your name correctly. Bishuwajit Gogoi. Tell me if that's correct or not.
Hello there, good afternoon. Yes, you're perfectly right. That's how you say my name.
All yours.
Yeah, can you please show the slide, please? Perfect. Hi, everyone. I'm a final year student of the Interdisciplinary Space Master at the University of Luxembourg. Thank you very much for having me here. Today, I'm here on behalf of our team, Nilufa, Fazane, Panayotis, and myself to briefly discuss our rethink of the ESA Rosetta mission by incorporating in-orbit servicing. Dr. Lavneesh Rana, lecturer at the University of Luxembourg, coordinated the team, and we were very fortunate to have the guidance of the project manager of Rosetta, John Eludin himself, throughout the study. Next slide, please. Rosetta was a path-breaking comet chaser mission, launched in 2004, and it took 11 years to reach its destination, Churyumov-Gerasimenko. During its nearly 8 billion kilometer journey, Rosetta executed a complex trajectory of planetary edges and even managed to squeeze in flybys of 2 asteroids for some extra science. You can see the photographs there of Earth, Mars, and also the asteroids as Rosetta did the flybys. However, with this long duration trajectory has its own pitfalls. A risky 2.5-year hibernation had to be done, which increases risk due to reliability. But at the same time, the actual mission also the instruments kind of become old because they're almost a decade after they have been launched. So can ISRU actually address these issues? The objective of our study was to understand the baseline Rosetta mission and investigate at least one ISRU use case scenario. Next slide, please. The first task of order we had was to develop a methodology framework. Starting at the top with scientific and ISRU requirements, we defined a launcher, ground system, spacecraft, and propellant depot requirements. These requirements, in conjunction with the constraints that we have from the mission parameters, allowed us to build a decision flow throughout the system. Trajectory design ran in loop with ISRU requirements, and this enabled us to arrive at a final architecture. Next slide, please. When we moved to trajectory, we had different optimization goals. Should we minimize the launch mass? That would reduce the launch cost. Should we minimize the transfer time, which would increase the science mission duration and also the reliability of the mission? Or do we just maximize the scientific payload, which in turn will increase the scientific output? For this preliminary study, we chose to focus on something simple, and that is minimizing the transfer time. We investigated a cislunar in-orbit servicing concept. We have from Earth to a distant retrograde orbit a propellant depot. Rosetta refuels at the DRO, and then from the DRO, we have a direct comet transfer. We did the entire trajectory modeling using CSpice toolkit of JPL NASA. Next slide, please. In parallel with the trajectory studies, we were also conducting a comprehensive literature review of in-orbit refueling concepts. Starting all the way from 1969 NASA reports, which first mentioned orbital propellant depots, all the way to today's latest OSAM report that was released in 2020 for the Artemis program. Next slide. With all these iterations, we arrived at a concept operation. We divided the entire operation into 3 phases: rendezvous and docking, propellant transfer, and propellant depot design, and proposed an overall system. Rosetta will be the chaser spacecraft and the propellant depot the target. A cone boom docking system will be used with refueling conducted with the help of a robotic arm. We take into consideration that Rosetta is not initially designed for refueling and has a bipropellant system. Finally, preliminary depot design is arrived at replete with all required systems for different phases of in-orbit servicing operations. Next slide, please.
1 minute.
Finally, we concluded that at the end of the study, that the key takeaway, we can potentially cut down the Rosetta's transfer time from Earth to the comet from 11 to 3.5 years with cislunar in-orbit servicing. However, this comes with major caveats, as direct moon to comet transfer is very energy intensive and will require changes in the spacecraft architecture. Good thing though is that now we have a methodology framework available along with a trajectory model and ISRU ConOps model to iterate the study further and test further potential scenarios. For now, the preliminary results of a simplistic ISRU use case model seems very promising. Thank you very much for your time and also this opportunity.
Thank you so much, Bishop Rajit, and it was really a very, very good, concise talk.